Welcome to our NSF-Simons Comic AI Weekly Seminar. I believe this is our third, is that correct? So it's my pleasure to welcome Mark Lacy. I've known Mark for quite some time. Mark, I think you got your degree in Cambridge, right? And then spent some time at Caltech, where I first met you over a decade ago.
Yes.
Which is crazy. Mark is an expert in AGN. In terms of other work, a lot of effort's been put in data processing and pipelining and archival science. And Mark has been the project director of the very large ARRAY Sky Survey here at NRAO, which has been a big undertaking over the last handful of years, and a lot of science is now coming out of that, which I think we'll hear a little bit about today. And a lot of this work you've been doing obviously is very related or to take advantage of AI. So excited to see about what you're going to talk about. Thank you.
Oh, thanks, Eric. So just on this title slide here, I just show off some VLA Sky Survey results. So on the left here, we've got the planetary nebula seen by the VLA Sky Survey. On the right is the optical image of the same bow tie nebula. Just to show that, in the radio now we are getting to the point where we can get optical light resolution over the entire sky. So this has been a massive challenge in terms of data processing. You'll hear later, which is why we need to start thinking about ways to improve the effectiveness of our processing by using techniques like AI/ML. So yes, how does this fit into the general cosmic AI project? So the themes of the explorable universe, the observable universe, the accelerated universe, and the explainable universe. And of course, we've fit in mostly to the observable universe part of this project. Data pipelines and data discovery in large data sets. PI is Eric Murphy for NRAO. And Ryan Loomis and Brian Mason are also closely involved. So what's the role? What do you think the role of AI/ML is at NRAO? Astronomers are typically focused on applications of AI for science, after all, but in the case of NRAO, we're interested in how observatory functions can be helped with artificial intelligence. Everything from proposal review to answering help desk questions, the data processing and pipelines, archives, software development, testing, and data queries. So we have a lot of potential applications with an overall goal, of course, of just trying to accelerate the process of scientific discovery while retaining accuracy and reproducibility. So I sort of got pulled into this thing of, we started having some meetings in 2024 to try and identify the use cases for AI/ML, and we picked them up again recently this year, just to see what we could do. So this is just a range of things that we thought would come in useful. So in this talk, I'm going to basically focus on observational astronomy and observatory functions. I'm not going to be very technical. I'm going to look at classes of problems rather than specific techniques. The layout of this talk, basically, I'll talk about what might be good problems to tackle with AI, interferometric imaging, our biggest use of computing, and how that could be possibly helped. Some summary of what we've been doing here, locally, various different projects that members of staff are working on. I'll talk a little bit about foundation models and finally finish up with some practical considerations. And I should emphasize that I'm not an expert, as has been very much a sort of effort where people have been looking into different aspects across the observatory and other places, and my talk has been influenced by a bunch of different people. I've highlighted Ryan and Brian here because they are involved in cosmic AI, but there are a lot of other people like Adele Plunkett, Dylan Dong, Brian Kent, the list goes on, and also people outside the observatory like Gordon Richards at Drexel, Francois Lanus in Paris gave a very interesting talk. So there's, but yes, these are going to be a bit of a mix of things. So what are our problems? So our problems are related mostly to the massive data sets that we are now getting in astronomy. The NASA has issues, but only on the sort of order 10 terabytes a year. JWST and the new Spheres, which launched, I think, yesterday.
Night,
so very exciting as an all-sky survey project in the near infrared. And then, but when you go to the ground, you're not constrained in your data rate anymore by the fact that you have to beam stuff down from space. So the Zwicky Transient Facility out at Caltech has a data rate of about a petabyte a year. The Vera Rubin Observatory, which the camera, it's a very timely talk because the camera for that I saw was just mounted yesterday as well. So that camera is now on the telescope and they will start taking data in a few months. And that will give us like 6 petabytes a year. The radio, we are not slackers here. ALMA's regularly churns out 300 terabytes a year. And there's a planned wideband sensitivity upgrade, which will push that up by at least a factor of 10, maybe a factor of 30 for the end of the decade. The VLA, chunking out petabyte a year. And then other radio telescopes at the Australian ASCAP telescope, which is a purpose-built survey telescope, manages something like 75 petabytes a year. And upcoming telescopes like ngVLA, our next generation VLA, and the square kilometer array will be getting to the close to 1,000 petabytes a year, pretty insane data rates. And so this brings many challenges, and just the sheer moving the data around and processing it is huge. And then, of course, these are going to produce huge finished data sets that need to be analyzed and science needs to be got out of them. So I'll talk about what do I think is a good problem? I mean, so there's, you can make the critique that you really need your science to be reproducible and accurate. And right now, the AI stuff is very much in development. There's a lot of constantly evolving algorithms and techniques and software that goes out of date in a few weeks. And so many of the things we currently do as scientists are not very well suited to AI. And if you've got the time and you have somebody who can come up with a good algorithm, and we have people here who can do that, they can probably beat an AI ML algorithm, certainly in terms of overall computing resources and numerical accuracy. But like I say, the data volumes and the complexity are getting to the point now where AI ML is probably the only feasible option in many cases. And that's sort of shown in the science side. This plot here is from a review paper by Smith and Geach in 2022, so it's already out of date by 2 years. But you saw even then, the number of papers using or mentioning AI ML techniques shot up basically exponentially in the last decade. So yeah, there's really is a lot of use cases out there. So I'm going to start with our language models and natural language processing. So we have people here, Adele Plunkett, for example, who's been working with some students from the UVA Data Science School on optimizing observation setups and pipeline parameters, just using proposal abstracts. So you take the words from the proposal abstract, try and figure out what the observer is trying to do, and figure out whether we can produce a setup that would work for their observations without having to go through a complicated human iteration loop. Brian Kirk in New Mexico has been just trying to use a language model to see whether we can ingest the guide for our software, the CASA software manual, and see whether it can answer routine help desk questions. And it does a pretty good job of that. Something else I think that's going to become important is natural language queries for archives. Write me an SQL query to find a certain type of data between these dates. It's for those of us who aren't very good at SQL or its astronomical equivalent ADQL, it's very useful to be able to have that sort of capability. And so the one project that I wanted to focus on here, because John Carpenter wrote up a very nice paper on it, is the ALMA proposal reviews. So ALMA gets like 2,000 proposals every year for review. And it's a distributed peer review. So the proposals are also the reviewers. And you need to figure out how to assign 2,000 proposals to many hundreds of reviewers. it's not an easy task. So previously they focused on using keywords. So in cycle 8 and cycle 9, which are the green and blue bars on this histogram here, the proposers and reviewers select a bunch of keywords, and the software tries to align the keywords of those proposals, and it kind of works, right? So when you do these reviews, you're asked to assess whether the proposal you're reviewing is in your field, whether you have some knowledge of the field, or whether you have little or no knowledge of the field. And this is getting it right about half the time. But you really want to avoid reviewers reviewing proposals where they have little knowledge of the field, and that was still like 10% of the proposals. So what they did was they used some machine learning techniques. They created a bag of words from proposal text. So that basically means you take all the words in the proposal and you basically reduce the words down to their roots. So you cut out all the modifiers, all the tenses, all the articles, and just have your bag of words. And then you try and assess how close the bag of words from a proposal is to a bag of words from a reviewer's proposals. And if they match well, then you can call that proposal a match. And it works surprisingly well. So you can see that the number of proposals where the reviewers felt that it was in their field went up from like 45% to 65%. And the little or no knowledge went down from like 10% to 5%. So this has been a quite effective use on the sort of proposal end of things. So for the numerical side, we often divide machine learning problems into two types of supervised learning and unsupervised learning. So in supervised learning, you start off with a large set of labeled data. So somebody has to go through and label like thousands of images or thousands of data sets, and then the machine learning model gets trained on those labeled data sets and then gets let loose on unlabeled data to see whether it can derive the correct labels. And that works pretty well. But the training set generation is expensive and labor intensive. And often it's sort of just for one specific problem. So once you've solved that problem, then you're kind of done, and there's not much else to do with it. So sort of, I think for the observatory viewpoint, we probably want to look more at unsupervised or self-supervised techniques, where basically the networks are doing, the machine learning networks are doing the sorting into classes. It doesn't necessarily translate directly into physical classes, like this rather amusing example here where you have the dancing animals. It sorts out which animals belong in which cluster. But I think in general it's going to work better for us. I mean, the one exception for this is citizen science. So there are citizen science projects where you get people in the community to label your data for you. But that in itself has some overheads. You have to set up that system for the data labeling and so on. So I wanted to sort of give you a tale of what we try to do with the machine learning for the VLA Sky Survey. So this is an example where we were looking for a specific type of anomaly in the data. So we produce 33,000 images over the whole sky. We produced them 3 times in 3 epochs. And the original data assessment was like a data analyst had to look, a human had to actually look at every single image, which was obviously not very practical. And so we tried to come up with some algorithmic and machine learning techniques to reduce that. And so our data analysts, so this was an entirely sort of homegrown project, bottom-up project from the data analysts, they came up with this, with a CNN method for basically detecting these, what we called black holes, primary beam holes, that's a more proper way of calling them, which are basically areas where the weighting of the image is gone. So this whole image is a representation of the sensitivity of the data. It's called our primary beam image, and that's 1 square degree on the side, and then this hole is where one of the telescope observations got weighted very low because there was a really bright source in there. And so this was able to detect these these images and the pipeline output, it was pretty effective. But we also developed an algorithmic technique which just looked for the numerical changes accompanied by these holes, and that actually worked a little better. So we actually kind of dropped the machine learning there, but it was still an interesting and useful lesson. However, the other people have also been using machine learning on the VLA Sky Survey data. So Brian Kent in this room has done this as well, basically using self-organizing maps to classify different sources. This particular example is from our Canadian collaborators, Vasquez et al. And basically the idea here was that you take your sources, our radio sources in VLAS are typically active galactic nuclei. So they are typically point-like, unresolved, or they're double, or they have more complex morphologies, which I'll talk about on the next slide. But these neural network nodes that you get from the self-organizing maps pretty much divide the data up pretty well into point-like sources, slightly resolved sources, and then this bottom corner and double sources. And then this bottom right corner here is where the anomalies are. So these things are not real sources with the big stripes on the bottom right. And so it's able to, any source that gets put in that neuron by the self-organizing map may well be an artifact of some time. So one thing they've used here, which is particularly important for astronomy, is that you need to have rotation and flip invariant augmentation of your data to get self-organizing maps to work well, because obviously a source at 0 degrees position angle and the source at 90 degrees position angle, which are otherwise identical, should be in the same neuron. So that was a useful thing they did there. And that's actually been added to the catalogs for some of the VLAS data. So you could say, you can tell which neuron is associated with the object and thus how likely it is to be an artifact. So self-supervised learning is kind of, as far as I can tell, kind of similar to unsupervised learning, but you do have a limited number of labels. So typically you only need a few hundred labels rather than tens of thousands of labels in your data set. You're basically doing dimensionality reduction. So you're taking a very high dimensional, in this case, pixelated image, and reducing it to a small number of latent dimensions. And you can use this for solving more general problems. And it drastically reduces the need for training. So this is an example, again, this is sort of focused on the anomaly detection use case. This paper by Lochner and Rudnick using actually not VLA data. This is data from the Meerkat telescope in South Africa. But basically the task here was to find things that look weird. And sure enough, like you see on the previous slide, most of our radio sources are kind of boring. But this algorithm finds these weird sources, and particularly useful if you're interested either in anomalies or in just unusual sources of some sort. So one of the questions I wanted to address with this these set of meetings was, can we address our biggest problem? So our biggest problem is interferometric imaging. It's the thing that keeps our computer racks hot, so that the sysadmins can fry their eggs on them in the morning. It really does use up a lot of compute power. And the reasons are that basically we have an array of, so I'm just taking the VLA, but ALMA is a similar use case, but it has even more antennas, like double the number of antennas as the VLA. But we've got these antennas, they're in an array, they are sparsely filling that aperture, and they gather data in Fourier space. So we're looking at the visibilities, the correlations of the signal between the antennas on the different baselines. And what we're trying to do is to basically take the sparsely filled aperture and try and reproduce the imaging we get with a uniform aperture that's the size of the array. So this is why it's a nightmare of a compute problem. So how do we tackle this? So the first thing you need to do is place your visibilities onto a regular grid. And this is actually the most computationally expensive part of the imaging. This is because it's not just a matter of taking points, you really need to convolve them with the Fourier transform of the primary beam. to do wide field imaging, you also need to take into account the curvature of the sky. So you need multiple planes. Basically, it's a 2.5 dimensional problem at that point. And we're getting GPUs to try and help with that, certainly for the VLA Sky Survey, but it's still a really computationally intensive problem. Once you've got the gridded visibilities, you can Fourier transform them into an image, and that's computationally fast. That's not really an issue. But then the next step is to deconvolve the images. Because of the sparse sampling of the array, the point spread function you get is pretty ugly, and you need to do a deconvolution task to recover an image that looks plausibly like the one you get from that uniform aperture. So this reduces, there are a huge number of possible algorithms for this. There's like 40 years plus of literature, people trying to get better and better algorithms to do this. But basically it reduces to a regularized maximum likelihood problem. I'll explain it a bit. And then once you've got that image, typically then we iterate. So we take that model image we produced from whatever process we used to do the deconvolution, we Fourier transform it and subtract it from the visibilities and start all over again. And this loop, this major cycle loop, happens somewhere between, typically about 10 times for a data set. So we're going through this gridding stage 10 times, which is one of the reasons why things are ugly. So how can we use AI to help with this? There's been a lot of ideas, both here and in the literature. So the deconvolution step is probably the easiest to approach. So the regularization, what we mean by regularization is you can take your visibilities and you can fit a maximum likelihood image to it, but the problem is there are an infinite number of those images. So you need to have some sort of prior, some sort of regularization, which sets the image up and makes the problem tractable. And typically, which is why I've highlighted it in bold here, the regularization function choice is that we believe that our images are basically made up of point sources or small Gaussians. Again, going back to that, if you remember that self-organized map, most of our sources are pretty simple, and that's a good approximation. But there are many other things you could do. You can specify smoothness, so maximum entropy, maximize the entropy of the image. All kinds of wavelet-based things, compressive sampling. There are a bunch of techniques. And you can also use AI for this. So you could base your regularization on other radio images, maybe simulations. We can also use AI to help with some of the decisions in the cleaning process. For example, this multi-scale clean, I said there are Gaussians of different sizes. How do you pick those sizes? You could use AI to help with that. Hendrik Muller, who's visiting, but I guess it's down in Socorro. Most of the time he is thinking about doing that. You can also teach AI the deconvolution. So you can give it the PSF, give it the image, teach it to do the deconvolution. That's this paper by Conrad in 2022. And then you could, in principle as well, use the text of the observing proposal and have them pick the most appropriate regularizer. So there are all kinds of things. I think that's just a lot of choices, a lot of things. Probably we just need to try out a bunch of things and see which works best. And then, of course, there's the perhaps bolder approach of saying, what if we just use an encoder to figure it out? So we take visibility data, we take the image, and we stick it through some sort of encoder. We train up the AI and see if we can get it to work. So quantitative, so I think right now, nobody has really tried this on real data with much success. Some people have tried it on simulated data. And quantitatively, I think, learning lessons from things like the AI learned deconvolution, it's a little questionable, but it might be good for previews. If you just want a quick preview and you don't want to wait a month for your data to go through the pipeline and get imaged properly, this may be a good way to do it. And you could also sort of train on the image. It might be easier to train on the Fourier transform of the image. The Schmidt et al. Paper does that. And I was kind of encouraged by this because you can sort of see structure in the image. One thing that we are going to face in the future, certainly probably for ngVLA, possibly for ALMA WSU too, is that we won't be able to send all the data through the pipeline and process all of it. It's just too expensive. So maybe you could give the PIs the previews, and then they can make a decision on how to spend the processing allowance that they've been given for their data. So yeah, so I'm just encouraged by this one because I can see this double source in the image here, and you can see these fringes in the Fourier transform of the image. Those are almost certainly from this double source. So you can actually see the fact that humans can see the image structure is, I think, encouraging that maybe this technique would work. So an open question is how many visibility image pairs would you need to train the network? I think it's probably more than we have right now. We've been running an imaging pipeline for the VLA for the past 3 years or so, but I think we're going to need even more to do this training. But it's worth investigating, I think. So some specific things that we are doing here right now. So in Cosmic AI, Brian Mason is looking at the calibration. I'll talk a bit about that. And then Ryan Loomis is looking at image segmentation and hyperspectral imaging. As I said, Adele is working on these natural language models to try and pull out science intents from proposal text. Vashi Rao, Brian Kirk, and Socorro are trying to get an intelligent pipeline. So they're trying to predict from the data, the visibility data, how the pipeline should be run, whether you need to flag bad data, things like that. And then there's also a big effort going on in astrochemistry. So Tony Remigin, Ryan Loomis, Brett McGuire, and their student Haley Scarlatti are working on using AI to help with astrochemical models. Again, a similar sort of problem that I talked about for the interferometry. If you want to do a full astrochemical model with all the reaction chains and everything like that, even for one molecule, it's really expensive, and then you've got hundreds of molecules in your molecular cloud. So what they've been investigating is using machine learning to take encoded molecular astrophysical environment data to predict abundances of both known and previously unobserved species in nebulae. So this is looking like a very promising approach. So the slides I pitched from Brian. So this is the calibration. So this is associated with ALMA calibration. So all our ALMA data runs through a standard pipeline, makes a web log contains many plots. The idea is that the poor human data analyst has to go through and look at each plot again, a bit like the VLAS use case I was talking about. And there were QA scores, and then we have our experts writing algorithms to improve those scores. But again, it's a very labor-intensive effort. But we got to the point now where about a quarter of the ALMA data sets can be delivered automatically based on QA scores. So somebody doesn't need to look at a quarter of the data. But we'd love to increase that, of course, and not the 75%. Yeah, the 75% that's currently reviewed by humans probably doesn't need to be. The tolerable false negative rate, though, is quite low. We do have a very, let's say, demanding, a very sophisticated user base who will spot if we make a mistake. So we want to make sure we minimize the number of false negatives. So here's a nice example. The idea is basically that this is a frequency dependent what we call a bandpass calibration, where you see that it looks fairly smooth. This is expected instrumental response that we're calibrating out, and then suddenly a dip here in the blue, and that's clearly something that's dropped out. It's bad data. So we want to be able to identify that sort of thing automatically, and also evaluate the consequentiality of these calibration features. Remember, we have 50 antennas, so a small defect on one antenna in a limited frequency range may not matter very much, but we just don't know. So that's what we're focusing on there. And then Ryan Loomis is looking at the imaging problem. Again, we're looking at in this case, it's looking at the ALMA database because it does have a huge set of quality assured images and visibilities. And so, so there are many use cases that we can think about here, reliably identifying parts of the tube that have signals or image segmentation issues. We've got overlapping lines in velocity space from different species. Separating out those is important. So I've already talked about the preview images, also use case for ALMA as well. integration by integration transient searches, localizing image domain effects, using the sort of anomaly detections, and then classifying detected structures as well. So that's what's going on there. And so I want to talk a little bit about foundation models. So these are things that, of course, in industry are very big. I don't think we're, I'll describe a few of the astronomical ones. So the basic idea of the foundation model is you don't just restrict yourself to one problem, you don't restrict yourself to one data set. You can have a bunch of data coming in different formats, text, images, structured data of various sorts. And you have your model, which does training, and then you don't make your model for one particular thing, you make it for a bunch of different possible applications, and you adapt the model for different tasks. So this is sort of different from what's been going on, I think, typically in most of astronomy, but it does require, these foundation models do require a huge amount of compute. I mean, we're talking about thousands of GPUs. So there have been attempts to do this in astronomy, including some very nice colorful logos, which I like the ALMA one, it's one of my favorites. And these are basically based on language models. ADS is working, which is our big preprint and publication catalog service, is working on something called AstroBERT, which is kind of similar. There's also a big effort called the multimodal universe. So this is taking tens, hundreds of millions of optical images, spectra, and time series, and putting them all into a big database and make it learn things. So there's some really nice things you can do with that. For example, you can give them the model a set of multiband images in the optical, and it will predict what their spectrum is. Or you can give it a spectrum and it will predict what the galaxy looks like. So there are all these kind of things that can be done with these huge models. But as I say, this particular one, I remember this is a talk by Francois Lanusse that he gave to the LSST group. He said it took thousands of GPUs to get this thing set up, but it is very impressive. So finally, I sort of wanted to end on some practical notes. So first of all, starting off with infrastructure. So I think, we have archives at NRAO and astronomical archives all over the US and other countries. But typically they're used to the user coming along and just wanting a handful of data sets, or interactively asking to download an image or two. And as those images get bigger, you get to the point of a terabyte ALMA cube or terabytes of the whole sky images. Probably nobody's going to want to actually do that very much. It's more going to be like, give me cutouts around my samples of my favorite class of galaxies for my ML training. So you're going to need a lot of highly parallel architecture and processing on the actual archive side. I'm not sure that people are there yet with that. It's certainly something that we're pushing for. But things like we might have to, our beloved FITS format, which is our observational astronomy's favorite data format, may have to go into something that's more hierarchical, like HDF5. These that the theorists use, these are things that we need to think about. On the positive side, I think there's another huge practical benefit in terms of AI-based coding. And even in the last few months, when people I've talked to and my own experience, the AI coding has gotten a lot better. And so this can be a great help both for our professional software developers, you can use them to say, write unit tests for this part of software, and they can test out all the different branches of the software and make sure that everything is good. But also for scientists like me, I don't want to look up Stack Overflow and find out the best way to do a Fourier transform of a 2D image. I will just ask Claude Sonnet to do it for me, and it will come up with something in it. This just took a few seconds to do, and it came up with something that was pretty good. And then I asked it to, instead of JPEG format for the image, can you do my version in FITS? And it came up a few seconds later with the correct version that worked in FITS. So it really is very impressive stuff. And if you haven't played around with it, I strongly suggest worth a try. Of course, there are issues associated with this, how to potentially maintain thousands of lines of machine-generated code in your code base if you're one of the professional software developers is something to be concerned about. And then finally, there are also the privacy, security, and ethical issues associated with AI. As an observatory, we do deal with proprietary information. Proposal contents are confidential, data is a proprietary period. On the technical side, there are issues of patents in our labs, like the Central Development Lab, and even possibly stuff that's restricted by ITAR. So we need to be able to make sure that when we're using AI, we don't leak some of this accidentally into the public domain, where the AI bots can just go and scoop it up. There also, as an observatory, we have to worry a bit about people using large language models to write and review proposals and papers. I think we need to be very clear on what's permitted and what isn't, particularly for proposals. And then attribution concerns. Yeah, as I'm sure most of you are aware, if you put something publicly available on the internet, it will just, AI companies will just harvest that data. So you need to be aware that that's happening. And then finally, there are also environmental concerns, of course, associated with the large language centers that generate, particularly the language models, these huge amounts of code that's not coming for free. It's a significant environmental concern as well. But having said all that, I think we can definitely make good use of AI ML in the observatory. So just to finish up, I think AI ML can be really helpful for many observatory functions. I think it's fair to say that in NRAO, there's still some way to go for acceptance. It's been more of a bottom-up approach here. People have sort of started their own experiments. I've been sort of leading these groups and Eric as well to try and sort of coordinate things. But it's mostly been a bottom-up approach. And I think there's a natural caution with such a potentially disruptive technology. But my glass half full approach is that the best applications of AI will free observatory staff from the sort of repetitive tasks that we all hate and allow us to focus on more interesting and productive activities. I think we want to focus on unsupervised and self-supervised learning where possible, because we just don't have the resources to produce large labeled data sets. And the exciting possibility is that it could alleviate our biggest computing problem, although I think we're still at a very early stage of getting interferometric imaging tools in AI. But again, the thinking is starting there. And the analysis and past the science of massive data sets, I think we're really seeing that can be improved with AI. And the nice thing about being part of the Cosmic AI Consortium is that we do have access to the AI/ML domain experts. I think that's really important, and I hope we can collaborate on some future projects. So that's it. Thank you for listening to my bag of words, and I'll take questions.
Right. So there's questions online, but first start quickly in the room. The people who are here, anything? Paul?
Yeah, I'll take a question, which is, you seemed kind of pessimistic about the possibility of having a pipeline that would be kind of just using encoders or some other sort of like flexible neural net type setup. You seem kind of pessimistic about that. I'm kind of curious if the why behind that is based off past experience, or if there's specific reasons why you think that might not be a viable approach.
I think my main concern is how big does the training set have to be. I think you could get something that kind of worked pretty well. And we do have tens of thousands of images now. But if you need 1 million images to make a training set of 100 million images, then that's going to be a much harder problem. So I think we just don't know is the answer. So, we'll hopefully, again, maybe we'll find out.
All right, one more in the room.
And just Brian, I had a comment, but just to tag on to that, I mean, another challenge is kind of community acceptance. Like, this is your image. It will be a high bar. So I think it's a good thing to aim for. The sort of quick look images, finding spectral lines and continuum, and there's actually a whole lot of niche imaging applications that would be super great for, other than making your final image.
Yes, I think that's the way
Probably
I'm
be
trying
easier
to,
than
I'm trying to
actually
sell it.
is.
Is, you know, it's a preview image. This
Yeah.
is not
Yeah.
science quality yet, but you know, maybe in 10 years' time it will be, right?
And it's
I mean,
probably
things
source
are moving really
specific
fast.
too,
So.
right?
Yeah.
Different classes of sources probably require at this point their own type of encoder and.
Yeah, so great overview, thank you. Just a comment on the unsupervised, self-supervised topic, that we do have 10+ years of operations data, and a lot of those problems essentially are, we have labels from operations, so those are good sort of supervised problems. There's one that I worked on with Ignacio, who's online, Ignacio Toledo, predicting QE0 pass due to good weather. We have all this, we have tons of data. So
Yeah,
there
that's a
are
good point.
there are
Yeah.
cases
No,
where
they
we effectively have labels,
Yeah.
because the whole observatory has been doing this for a long time.
Yeah.
We sort of know things. But they are more on the operational side, not like the imaging side or the science side.
Okay, taking a question online. I do see Stella. I see your hand.
Hi, Eric. Hi, Mark.
Thank you.
Yeah, so I had a question about the proposal review, which I didn't realize you were doing that for the ALMA proposals. And maybe it's not really so much a review as proposal classification and sorting approach, but also to tie into what Brian said about community adoption and the general skepticism. I think that seemed like a very plausible and exciting application of AI. And I was wondering how widely you distributed the knowledge that you were doing this. Did you tell the reviewers? Did you tell the submitters that you were doing this? Because I think there is a disconnect in acceptance. People don't really understand how the AI is being used and don't really see and understand the success cases.
Yeah, that's a good point. I don't think that was being sent around with to the reviewers. So I don't remember seeing it when I was a reviewer, let's put it that way. So it's maybe a good point. Maybe we should be advertising this a little more brazenly.
Yeah, I think really highlighting success cases is really an important step for community confidence.
Yeah.
And that doesn't seem like something that would get people all upset about. So
No.
yeah. John?
Yeah, thanks, Mark. I enjoyed this. I was wondering, so in this slide, you say that one of the motivations is to get rid of repetitive tasks so they can do more interesting things. I'm just wondering, is the overall goal, and maybe guess the answer is that there's not going to be one overall goal, is a better product or such. And I'm just wondering how tractable the trade-offs are in terms of cost effectiveness. Is it very easy to say what the cost of an AI trained result is versus what it would have taken to have done it in the standard way? And the compute access, the the energy consumption, the FTEs, et cetera. How tractable is the cost of AI?
Yeah, I don't think we could do that for small projects like the VLAS example I talked about, where we compared the AI and the algorithmic model. But yeah, for bigger problems, I think it would be very hard to assess that. Yeah.
Not linear functions.
Yeah.
Is that something that people who are doing, maybe this is more for the data scientists, is that kind of cost and cost benefit, is that typically done when people apply techniques, or is it just like, well, we just want a better answer, and so it doesn't really matter? Right.
It's a hard question.
Yeah, it's our question.
It's a good question.
Yeah.
All right.
I have an opinion
They can add
there.
it to the
if
chat.
that
If
is-
somebody knows, they can add it to the chat.
Ignacio, your hands up.
Yeah, can you hear me?
Yep.
Yeah, so I was just going to tell to John, yes, yeah. From what I have seen, well, one of the options when you want to use AI and machine learning is basically, is there something that if you have an army of people that would work with you, would be able to solve sorry, let me put it. There is something that you can do that you can solve having an army of people that could do for you, no? And AI machine learning could help you solve the same thing by not having to hire a lot of people and spend a lot of human time solving an issue. So I think that one of the metrics that you have to apply is not only computing cost, but also how much of this extra work that it will cost you to hire an army of people to solve a problem would be solved by the use of machine learning. So I think that also needs to be taken into account.
Absolutely, that's the other side of the balance sheet is the
Yeah.
FTEs but then you also have to kind of value the improvement or decrement in what you're providing.
Yeah, but that has to do, I think, a little bit with if you could hire 100 people to solve a problem, it means that problem means a lot to you. So I think in that way you could get with some metrics to say how useful is a problem that you're solving. Just an idea, or that it's not my own idea, but I think that's one way of actually creating some metrics.
Niall raised his hand.
Well, I was going to soapbox just a little bit here, but I think, I mean, especially in the generative form of all of this right now, but I think it's true across a lot of the machine learning that's, using sparse matrix algebra. There's a lot of inefficiency in that hasn't really been accounted for because it's not like the same sparse matrix algebra that you do when you're doing computational fluid dynamics. And so, right now, the Googles and everybody in the world are just throwing money at the problem, which, they think is going to solve it. But, DeepSeek came out and they did some optimizations and it got better. So I think, really what we need to focus on here is making it effective, figuring out how to adapt these things. But I also just, these things are too expensive to train in the current model. And, we here at TAC and other places are going to be focusing on that over the next decade to hopefully make it so that we can take all of, the reduced ALMA data and teach it to do, the transformations that are needed to get it there. And maybe in 10 years, get it to be the same level where, with a space telescope where we introduced, on the fly data reduction and people said, no, it'll never work. And 6 years later, nobody downloaded raw data anymore. So, I think we're in that transition phase here when it comes to how AI and ML will really impact things. And I'm looking forward to seeing where we get to in the Institute.
Yeah, thanks, Niall. I think I tend to agree with you. Omkar.
Hi, yeah, I was just wondering, one aspect you didn't touch upon is really, can AI be used for like the like standard calibration of visibilities, like amplitude, phase calibration, and solving the gains basically with do you see a potential there as well?
So I think, the standard calibrations that we do are pretty, and the nice thing about them is they do run pretty efficiently with just algorithmic techniques. As Brian is working on this, looking at the QA side. There's also RFI, and I think that's just something I should have talked more about, which I forgot to do. Because yes, there are also AI ways of finding and excluding RFI at the calibration stage, which I think could be a good use. It's something that's, it is much more complicated than just fitting a complex gain or something like that. And that could be a good use of AI, yeah.
Okay. Any more questions from folks? All right, if not, then let's thank Mark again.